Hey everybody. Thank you so much for coming to my talk. I'm very excited to be here. And I am here today to talk to you about this thing, which is a wearable live captioning mask that hopefully, as you can see, is live captioning what I'm saying. It's got a flexible LED array inside it, which is mounted actually inside the mask. But you could perhaps put it on a t-shirt or on a bag or some other wearable item. But before we delve into the tech, let me introduce myself. My name is Jo Franchetti, and I am a developer advocate at Ably. And Ably is an edge messaging platform which helps developers like yourselves to build live and collaborative experiences. We have a whole suite of SDKs and APIs that give you the freedom and flexibility to power apps like chat or delivery tracking or multiplayer games or collaborative document editing for millions of connected devices at the same time. And I'm primarily a web developer, but I do also occasionally dabble in IoT. I put LEDs in my wedding dress, and I made a Christmas jumper that displays a different graphic depending on what Christmas tune is playing at the time. And I have to admit to a personal desire to see more products like this on the market. And that personal reason is because of my mother. So this is my mum, Mama Franchetti, and she's a smiley, sociable, quick-witted woman who loves a good natter with her mates, but she's also been steadily losing her hearing over the last few years. She went to too many rock concerts when she was younger, and losing her hearing has been an incredibly isolating experience for her, as I'm sure it is for many people. She relies heavily on lip reading and clear enunciation. And you know what makes lip reading and speaking clearly impossible? Wearing a mask. So if she was struggling before Corona hit, everybody wearing a mask has made it almost impossible for her to go about daily life. She can't socialize safely with her friends and hear them at the same time. She can't understand people in shops. And people have a tendency to become rude or brush her off when she asks them to repeat themselves. She gets quite self-conscious about it, and occasionally she'll just try and style out having not heard you at all, and you'll be like, "Mum, you didn't hear me, did you?" And she'll be like... So I have a couple of asks for you during this talk, and the first one is this. If anyone ever asks you to repeat yourself, please don't say, "Oh, never mind," or "it doesn't matter." It's really frustrating being able to hear only half of a conversation. And as we've traversed her hearing loss, one thing's really struck me, and that's that as developers as a whole, we're really not doing the best job we possibly could at making assistive technologies and making what we call aging technologies. My mum has a cochlear implant, which is a really cool device. It's a processor inserted directly into her head, and it has a little battery that clips over the top. And she can stream audio directly from her devices into her head. She doesn't have to wear headphones anymore. Like, super cool. Like, my mum is a cyborg. But do you know what happened? So first of all, the app only runs on iOS. Don't know why. Why is their development team not able to make it run on Android as well? So she had to swap phones. And a year ago, iOS released an update that did something incompatible with the app, and everybody who had this particular cochlear implant had a screaming noise streamed directly into their head for a whole day until an update was released. And we just really need to do better than this, generally. I know assistive technologies aren't very sexy, so they don't get the attention that the more glamorous engineering jobs get, but goodness, we can't be screaming into people's heads for a whole day. So my second ask of the talk is this. Let's put a little bit of effort into accessibility and think about our fellow humans, and let's make some really cool assistive tech. So story time is almost over, I promise. But I was really worried for my mum. She felt even more isolated than the rest of us did during lockdown. And assistive technologies that run on her phone meant that she had to be looking down at her phone as she was speaking to people, and people often thought that meant she'd clocked out of the conversation or was busy, so then they'd turn and start talking to somebody else. So I wanted to build something that she could wear, or that we could all wear on our faces, so that she'd be able to read what I was saying and look me in the eye while she was speaking to me. And, we're all developers, we like to solve problems. I wanted to be able to fix this problem for her, and inspiration struck me at the weirdest of places. I was in Cyberdog in Camden. If you're visiting London for NDC, it's well worth giving Camden Market a visit, and there you will find this shop, which is called Cyberdog, which sells primarily rave gear, so stuff you can wear to raves. And they were selling this thing, which is a mask with LEDs in it. And the next slide has some animations and some flashing. I realize this content warning is a bit redundant when this is right here. So it had a high enough resolution that it could do these really cool animations. And I bought one immediately thinking, what if I could put text on there? I could signal to my mum what I was saying so that she could look me in the face as she was talking to me. But the display in the mask came with a built-in processor that came with its own Bluetooth app that was written in Chinese that I absolutely could not backwards engineer. Trying to sniff the Bluetooth was a nightmare. I checked how the mask was wired up. It was very clever, but very unintelligible to me. So not wanting to be beaten, I thought, I can make this myself. So if we break the mask down into its component pieces, then what we really need is a flexible LED array of some kind made up of addressable LEDs. And when we talk about addressable LEDs, what we mean is that each LED in the array has its own numeric address so that we can send data to each LED individually. We need a way to control these LEDs, so a small microprocessor board of some kind, and we will need a small battery that we can hide somewhere on our person, which is going to power the board and the display. All of these things need to be small enough to fit in a wearable, and then we'll also need a microphone that can pick up the speech, and we'll need some software that's going to do the speech to text. So the LED array that I have in here is one that I soldered up myself from LED strip. It's 28 by 8 array of neopixels. Neopixels are just very, very small RGB LEDs. They have their own little tiny processor on them, which makes them addressable and makes it possible for them to show any color you could possibly imagine, sent with an RGB value, very similar to what we see in CSS all the time. And it's flexible to a certain degree, and it can have small holes put in it for breathability, and it can be powered by a really small microprocessor, which is this thing here. This is the ESP8266, and it's very small, so it can just about fit in a mask. It can be powered by a USB battery, so I'm using this thing here, which is a lipstick battery. It can easily fit in a pocket, and that'll power the mask for about an hour. It has Wi-Fi on the board. You can see that windy bit down the bottom is the Wi-Fi antenna. And I could have got a tiny little microphone and soldered that onto the board, but honestly, doing audio streaming plus controlling the LED array is perhaps a little bit too much for this tiny board. But as I said, it does have Wi-Fi, and we all carry phones around with us all day, every day. So why not outsource the microphone to the phone instead? I can make a web app which runs on the phone, which will take the audio, do the processing, and then send the returned text back to the microprocessor, which will then display it on the array. So I used Azure Cognitive Services to do my speech to text. I made a web app which is using Azure Cognitive Services. Under the hood, Azure Cognitive Services is using the Get Media API, and if you've not used Cognitive Services before, it's a suite of APIs which allow us to add AI capabilities to our apps. And one of those capabilities, obviously, is speech to text. So the web app that I built is a very simple Node app. It uses a few different Node packages. So we have the Azure Cognitive Services Speech SDK. We have a driver that I had written for a previous project, which I extended a little bit for this particular project, which is the driver for the LED array. And then we're going to need some sort of transfer protocol to get the messages from the app to the board. The app itself is really basic. The UI is quite boring. Here's what it looks like. We have a button to turn on the mic and start streaming the audio. We have a box which shows the returned text as text. And then I have a visual representation of my LED array for debugging, because it's a pain in the ass when you have to re-upload your code to your microprocessor, and that takes 5 minutes, and then plug in a battery and all the rest of it. So this visual version of the board, really useful for debugging. And then I also have some settings for color and for scroll speed. So let's start by hooking up the Start Listening button and sending some data. So I wrapped the Azure Cognitive Services SDK with this code here. So as I mentioned, under the hood, the ACS speech-to-text API is using Get User Media. Get User Media has been in browsers for years now. What it does is it prompts the user for permission to use their microphone, their camera, and once allowed, it will start to collect a stream of data from their media devices. Obviously, we're only using the microphone here, so when I open the app on my phone, it will prompt me for microphone usage. And so once we've hit that Start Listening button, a function called Stream Speech from Browser is called. And this uses Azure's from default microphone input along with an authorization token function, which will authenticate with Azure and initialize this speech recognizer. And the speech recognizer is what is going to perform the speech recognition. And this will return an object which contains the text of what it is that's been said, so what's been picked up by the microphone. And then I wrapped the Azure Cognitive Services speech SDK again with a class to provide it with an API key. Then I register a callback on text recognized, and we will talk about this a bit later. The callback calls the Matrix LED driver, but for now, let's talk a little bit about communicating with the hardware itself. So how do we get the transcription? Once we've got it back from Azure Cognitive Services, how do we get it from the app to the microprocessor? We need some kind of messaging protocol, and there is one that is used for IoT devices, which is called MQTT. It's a lightweight publish and subscribe protocol designed specifically for IoT devices. It's very high latency. It works really well with unreliable networks, which is great because who knows, we might be on a 3G connection. And in order to use MQTT, we will need some kind of broker. And this is the service that is responsible for dispatching messages and making sure they are received by the correct recipient. So in this case, the web app is the sender or the client, and the microcontroller is the receiver. And I work at Ably, so I used the Ably MQTT broker. The great thing about the Ably SDK is that we can use the JavaScript SDK in our web app, and it automatically sends out messages over MQTT as well, so all of this work is already done for us for free. As I mentioned before, the microprocessor is really small, which means, unsurprisingly, it has quite limited processing power and very limited memory as well. So that means that the code that we run on it, we want it to be as efficient as possible. So we want to avoid doing complicated things like text parsing or other similarly memory-intensive tasks. So parsing and splitting strings is going to be quite costly. It involves larger buffers than would really be ideal to run on a microprocessor. And you might be thinking, this sounds like premature performance optimization, but if all of the memory on the board is used for passing the messages, it decreases the amount of memory that we have available to buffer incoming messages. So to solve this problem, I used a binary messaging format which will talk to the hardware, and the browser app is going to create a specifically encoded message to send strings to the device. So let's have a look at that here. Most systems that you would write would probably use JSON to serialize messages. Instead, this app uses a binary format. So the order of the messages and the content of the bytes as they are received is relevant to how the hardware is going to process the text. So let's say, for example, if we wanted to scroll text on the display, we might send a message from the browser that looks like this. But rather than sending it as JSON and then transmitting that as text, we need to encode the data to pack it down into the smallest message that we possibly can. And we want to be able to send those messages as raw bytes. So I'm using here some control codes from the ASCII standard to provide header information in the messages that I'm sending. And because the message is a raw byte stream, we don't need to then do extra parsing of the messages on the hardware. It can just loop over the message bytes and run different processes depending on the byte that's being looped over at the time. And this is awesome because it takes the complexity of parsing text away from the microprocessor completely. All of that is done in the JavaScript code in the web app, which is much more capable of doing that work. And it's also much easier to debug and to test. So if we have a look at the table above, we have, for example, a byte at offset number 8 would represent a single character, but the parser on the hardware is looking out for the STX and the ETX, the start and end markers. So what this means is that we can send any number of ASCII characters in the space between those two to form a full sentence or a message. I don't know how many of you have worked with hardware before, but it is notoriously slow and difficult and frustrating, especially when you have to flash the ROM of a physical device, power it up, look at it to test your code, and sometimes running in the Arduino software is just quite frustrating, although I'm told VS Code now can run a whole load of Arduino stuff, so that's cool. So to combat this, in previous projects, I'd already written a separate NPM package, which is the matrix driver to try and solve the various quirks of the hardware. And it's this same code base that I'm using to scroll text this time, but in previous iterations, for example, I made a t-shirt that you could basically do MS Paint on. So I needed to be able to send individual pixels worth of data. And then for the Christmas jumper, it was sending entire images. So this driver can do a whole load of different things, but I needed to extend it to scroll text, which I will talk about in a little bit. But for now, let's take a look at actually hooking up the speech recognition first. So earlier on, we registered a callback to onTextRecognize that called the matrix driver. What we didn't look at is how we then connect the browser to the LED driver using Ably as the MQTT broker. So there's a few things going on in this code. First of all, we are making an instance of the Ably JavaScript SDK. We new up an instance of the remote matrix LED driver class, and that's just part of our display driver package. It takes a display config, which tells the driver how big our display is, and it also needs to know what transport we're using, so the implementation of the encoding protocol that I just mentioned earlier. So this feels like a lot of stuff, but what it means is that when we call the functions available in the matrix driver SDK, it knows how to convert pixel locations into absolute numbers that the NeoPixel hardware understands. So if you think about an array of LEDs, which each have a number on it, it's able to convert between a matrix into what is basically a straight line that snakes through the hardware. And it knows how to transmit the data over MQTT. So finally, we need some code for the microprocessor that understands this protocol and converts the packed binary data into calls to set those individual NeoPixels. And just if we were to visualize the entire system, this is kind of how it would look. So let's talk about how we send those compact messages and take a look at the display driver and talk about how it reads those messages. The LED array driver, as I mentioned, was written for a previous project, so it already has some cool API calls. So it can set an individual pixel with a single color, and you can set the color in hex or RGB. We can also set it using just the X value. So imagine if we had a string of light snaking through, it'll assume that the Y is 0, and we can just set a single number. Or we can also set the entire display at once using this sort of visual coordinate array, which is super cool. We can even send entire images to the display, as long as they're small enough in pixel size to send. The Christmas jumper that I made was 16 by 16. Trying to make little Christmas emojis at 16 by 16 is a fun little task. But we want the driver to display scrolling text. So we extended it to include a new API, text.scroll, and we also want to potentially give it a color and a speed setting. So let's talk about how these new APIs work. The first thing that I had to do in order to show text on the board was design some kind of pixel font. This was a vague guesstimate at the characters that I would need to use most regularly, although I am now sad after having talked to some people here that I didn't put little emoji smiley faces in. That's a future upgrade. And then I converted each of the letters in the array, each of the letters in the font to an array of pixels. So let's take the letter N as an example. If we convert this into binary, it's going to look like this, where each of the off pixels is 0 and each of the on pixels is 1. And the final array for the character N will look like this. And here again is that array. And what we've done is we've now got the 4x8 block as a single array. But instead of encoding the entire alphabet by hand, because that would have taken a very long time, there's a JavaScript image manipulation library called GIMP, which will actually do this for you. It converted the PNG of the font sheet into a long array containing each supported character. Thank you very much, GIMP. And if you look at the font image, please imagine this is a long line of letters. I've taken liberties with slide designs here. You may have noticed that the characters aren't all the same width. And I did this because I think it looks nicer, slightly more legible, slightly nicer kerning, which is important. But it means that the array of bits for each letter also needs to have a width, so that the board will know where the starting position of each character is. But that's just a little bit of extra data. So we have an array now of starting positions for each letter, and we have an array of each of the letters. And these 2 byte arrays are small enough to actually be stored on the board itself. And with this font array embedded on the device, it's possible to write code that then shows the letters as they are sent. This means that instead of computing all the individual pixel positions in the browser app and sending them one by one, the microcontroller can actually handle that translation, which means that we don't have to send the extra data over MQTT, which is great because we want to keep our messages as lightweight as we possibly can. So cool, now we have a font. We need a way to work out how to display that font on the array. And as always with hardware projects, nothing is ever as simple as you want it to be, because there are multiple different ways that LED arrays can be connected together. So because I soldered up this one myself in the mask, I know that that is created in a snake that goes horizontally. However, this one that I bought here is connected in a snake that goes vertically, of course. And we can also get displays like the one shown in graphic 1 there, where the wire snakes right the way back, so it's sort of in reading order. Not only that, but displays also usually have connectors at both ends, which means that the numbering could go from left to right or from right to left, top to bottom, bottom to top. It depends entirely on what display has been bought, and I would like other people to be able to take this and run with it themselves. So I needed to encode a whole load of variety of wiring patterns. We need the board to be able to translate from XY coordinates to the appropriate pixel ID so that any developers who want to make one of these themselves can do so. So once the coordinates are sent to the hardware, it can translate the coordinates into the correct pixel ID based on the configuration that we sent earlier when we told it how big it was. So we set up some configuration on the board, like this. This is our configuration file, which contains which pin on the board we are sending the data out on. It contains the width and the display height of the board, and then where we've connected in the first LED, what kind of snake mode we're using, and what kind of NeoPixel it is. Now, this has caught me out on previous projects before. There's two main types of NeoPixel, RGB and RGBW. RGB takes 3 colors, RGBW takes 4 colors. If you mix up the type that you got, you get some very odd things happening on the display. Don't let that one catch you out if you are doing NeoPixel projects. So, when the message arrives at our device, it runs through an initial parsing block that interprets the message that the LED driver sent. It checks the first byte for the control code and the second byte for the control mode. So are we sending text? Are we sending a picture? Are we sending individual pixels? And then so if we get a T, then we know that we are sending text to our hardware. And the microcontroller software is then able to set the individual pixels and display the font that is stored as variables in the Arduino code. The missing piece that we haven't got yet is message handlers. So the handlers are going to have to process the incoming binary messages, look up the font data that's stored on the board, and then push the appropriate pixels to the display. And you can see on this slide that the text display code parses the bytes in the order of the table that we talked about earlier. So if you remember this little table here. So when a message to display text is received, the code loops through each text character in the message and looks up that character in the embedded font, which is on the board. The font data then gets returned. The font data that is returned from the font is the array that we saw earlier, so like the letter N, for example, prefixed by the width of the character in pixels, and we will also add in a little space in between each letter, which is just a bunch of zeros. Because the font data includes the width, when the code iterates over subsequent characters, it can then calculate where it needs to start drawing at when we're showing a word on the screen. So if we call the location of the left edge of the letter the X position in the code, each time a character is drawn on the display, we increment the X position till we know when to draw the next letter. And as the code loops, all of the XY coordinates are returned from the font. We'll all have this X position, making sure that the characters are drawn in the correct sequence. This will continue until X position hits the width of the display, and then we stop because there's no point in rendering characters that we can't see. So that will write text to the display, but we also need to scroll it. And scrolling the text is pretty much exactly the same, but the X position is going to start out at the right-hand side of the display and move across to the left. So when a message is first received, the X position is going to be equal to the full display width, so no pixels will be drawn, as you can see in this top graphic here. Then we increment the loop and decrement the X position by 1, and we keep going through that loop, decrementing until the X position becomes minus the width of the board. So say we had a board that was 100 wide, it would be minus 100, which will scroll the text all the way across the screen. And you can see the code for that here. So if the message mode indicates scrolling text, we start a while loop that updates the scrolling position in the byte array, and that represents our entire fonted string, so whatever it is that needs to be displayed, and then starts looping, and it'll display a subset of the total data of the string until the final pixels are scrolled off the screen and we see all of the text. The cool thing is that as the animation is played, the code pauses execution every time it scrolls, and this loop prevents control from being returned to the main Arduino app, which would then trigger receiving MQTT messages, which means that the code on the hardware only ever draws pixels for the characters that will be visible on the display. Memory is saved by not converting every character into pixels ahead of time, and we can use MQTT itself as a buffer without having to use up memory on the device. So once we finish scrolling, we can then receive subsequent messages from MQTT itself and start scrolling the next piece of text. Whew, okay, that was a lot. So I see my mask has stopped listening to me. I wonder if that's because my phone has gone to sleep. So that is how the mask was built. This is me and my mother attempting to communicate. She was a little foxed by the entire process, but seemed to be impressed. But there is more. There's more stuff that I haven't spoken about yet. So we would be here all day if I told you every single part of the app. But one of the things that I haven't mentioned is if you don't have an LED display, which, I understand most people maybe don't, we also have the text displayed in the app. So if you just want to be able to share your text with somebody else, you can actually press that little share captions button and it'll just send them a screen with the text on it. So we're back in that place where someone is having to look at the phone to hear what you're saying, but not the worst, better than nothing. This is possible because we're using Ably, the messages that we're sending out are sent out over WebSockets as well as MQTT, so we can have as many people as we want sharing our subtitles. The other thing that I've not mentioned is the visual representation of the display in the app. Behind this is basically an emulator of what is happening on the Arduino that is built in JavaScript that's running the same code that we're running on the board, but outputs in divs instead of in RGB LEDs, which is so awesome because, as I mentioned, debugging hardware is long thing. But I won't cover it today because I'm sure you've already heard enough of my voice. But the good news is that all of the code for this project is available on GitHub and it's all open source. I would love to see you make something with it. I would love to see more people make this kind of thing. If you go to github.com/ablylabs, there's also a whole load of other useful demos. So if you want to build IoT projects, you can take a look at my LED wedding dress that's there. The Christmas jumper is there. If you want Microsoft Paint on your t-shirt, that's in there. If you're building a chat app or if you're building multiplayer games or collaborative whiteboards, anything that requires data to be sent in real time, there's a whole load of open source demos that I've written, which are available for you to take away and turn into your own thing. And if you do decide to try out this project or any of our other demos, please do tell me about it. I would love to see what you make. And if you're working in assistive technologies, I would love to hear about what it is that you're doing. You can get me on Twitter at thisisjoefrank. We also have an Ably Discord, which I've just realized I've forgotten the link. But if you would like to chat with me on the regular, you can come and find me and get the link to the Discord. I'm always happy to talk about real-time projects, and I would love to see what you're building, so give me a shout. I have some stickers over here. They're really cool. Come get a sticker. And thank you for listening, NDC. And if you want to come try out the mask.